And then I guess let's just give it a couple more minutes, but this might be the group that we have here. So good to see everybody. Glad to see your cameras are all on.
I know. I just came out of like a 3-hour meeting and
oh, 3-hour Zoom meetings are the worst.
Yeah, I know. It was a long meeting.
So bad. So it's interesting.
Yeah.
Sorry, go ahead.
Go ahead.
Oh yeah. So did you hear the convention center fire that happened here like last year?
The convention center?
Yeah, so there's a convention center that's not quite finished. The span is like 250 feet long trusses. So it started on fire, and the roof started on fire. And what they're having us do now, I'm part of this project where the engineer of record's kind of scared that maybe the fire did some bad things to the trusses. So we're part of this project where we're actually going in and we're yanking down on the roof trusses.
Wow.
Made me think of it as I was in like a 4-hour meeting yesterday about that on Zoom.
Wow.
Yeah, man, it's gonna be pretty sweet.
Wow.
Cool.
That's crazy. Yeah. So do you know what caused the fire? Is it like a?
So nobody's confirmed it. The unofficial word is somebody left a blowtorch on. So the roof was made out of this weird material. It's like straw almost. It's like panels that are filled with straw. And apparently somebody went on a smoke break and they left a blowtorch on is the unofficial.
Oh, wow.
Yeah. Yeah, that guy's in trouble.
Well, straw is, I guess it's flammable, pretty flammable.
Yeah, dude, they had like the entire North Island Fire Brigade there for a week. There's still cars. So there's mold everywhere, and there's still cars in the parking garage in the basement that are, because the basement's complete.
Oh, they're stuck, probably.
Yeah.
Wow. So what did you tell your insurance company? My car is stuck in some parking garage. Yeah. Caught on fire.
Exactly.
Wow.
All right. Well, why don't we? It looks like this might be it. So thank you to the 6 people that have showed up. So we have a special guest today, Nasser Marafi here. Let me see. I had his email up so I could get his actual title now. So Nasser and I did our PhDs together at the University of Washington. You graduated a few years ago now. When did you graduate?
I finished my PhD in August 2018.
August 2018. Then you did a postdoc at the University of Washington.
I did a postdoc.
And then now
at UW.
Now he's a senior modeler at Risk Management Solutions, which is insurance. What do you guys do?
We do risk modeling
makes sense
for insurance companies and reinsurance companies and all kinds of clients. And so, yeah.
Cool. And so Nasser's done a whole bunch of work with OpenSees and working in Python. Actually, Nasser's the one that got me into Python. So before I hung out with this guy, I was just a poor slob trying
all MATLAB.
MATLAB. So
all MATLAB. We would have like fist fights about OpenSees, MATLAB, OpenSees, MATLAB. And it seems like, I don't know who won.
Yeah, Python won out, certainly. So what he's going to talk about today is some of the work that he did in his PhD, focused on the Cascadia subduction zone event, which is an M9 event in the Pacific Northwest of the United States. And I think we're going to talk about the effects on like some shear wall buildings or something. What Nasser said before you guys got here is during the presentation, if you have any questions, just speak up. I'm guessing because there's so few of you and you don't have your cameras on. We'll see. We'll see if that happens.
So how about this? How about this? To get people to speak up or encourage them to speak up, let's have why don't each person who's attending unmute for a bit and just talk about, who they are and what they're doing at University of Auckland, what their research is about. Just so that I can, I'll try to tailor my presentation to the people that are here as much as possible. I have 40 slides. I don't want this to be a one-way presentation. I want you to, unmute, ask a question the minute you come up with it. And like, talk to me about my struggle. Like, tell me, like, what are your struggles in OpenSees? How did you solve this problem? How did you solve this problem? How is this modeled? I have 4 or 5 slides about OpenSees, but I typically go pretty fast on them just because no one really asks a lot of questions. But since this group is really, they like to get their hands dirty with OpenSees, please do stop me and ask questions. So let's start off by just, so each person unmuting and just telling me about their research and what they're doing at the University of Auckland. So maybe Nanish, yeah, you're unmuted. How are you?
Yeah, very well. Thanks a lot for presenting your research and presentation. I initially started with the, is my voice audible now?
Yep.
Yeah, no, I can hear you. I can hear you.
Yeah. So initially I started with modeling a triaxial test. So it's mostly with the geotechnical side of using the OpenSees PY. Then I went on to model how do you incorporate dilatant behavior. It's a specific sort of behavior for soil, especially rock type of materials, which helps us understand that just before you keep on intensifying or densifying the soil, there is a small range of loads and strains, stresses and strains, in which if one can tap into that, there is some additional efficiency that is generated for the entire structure. So that's what I initially modeled for OpenSees TCL. Uh, then for the graphical interface, we used OpenSees PL.
Yep.
So that's specifically for points. So that was my research, and the outcome was that there was the dilatant behavior does help to increase the structural efficiency. So that was my model.
Cool.
So you'll see in today's talk, you'll see some, I'll talk about some basin effects and so how they affect structures. So that's the geotechnical aspect of my presentation, and you'll find it quite interesting for your area of research. How about Claire? Claire, we can't hear you. I don't think your mic is working.
My mic sometimes does not work. I just removed my headset. Hi, kia ora, I'm Claire. I'm a second year PhD student. I'm working on hybrid structures with steel frames and concrete walls that are joined together. So what I'm doing, I've never actually touched OpenSees TCL. The thing is, I've been working, I used to work on Python for several years. So when someone told me that, okay, you're gonna use OpenSees, then I jumped immediately to OpenSees PY because I knew Python already, but I'm not very knowledgeable at OpenSees Py yet. I've been tinkering with it for a couple of months, but on and off. So yeah, I've been making some models and things like that, but nothing much has happened yet. And then, so because I'm working with steel frame concrete wall hybrid buildings, I'm also going to do some experimental tests on the connection so that I can get, moment curvature curves and things like that to integrate into my model.
Cool. How about Roy?
Hello, I'm Roy.
Hi, Roy.
Yeah, I'm a PhD student. I'm a visiting student in University of Auckland, and my research is about precast concrete wall. Yeah, the same as you, Nessa. So I'm very curious about your research in different Squeak Zoom. I'm learning OpenSees PY for about a year, and now I'm modeling the connection of my precast wall. Yeah.
Cool. Where are you visiting from? What university are you visiting from?
I come from China. Yeah. And my university is Hunan University.
Okay, cool. How about Sean? Are you there?
Yeah. Hi.
Hi, Sean.
Hi, Nasser. I'm a PhD student. I'm working on bridges, modeling. I'm modeling to study the model characteristics of bridges in earthquakes, and also doing some starting to do some nonlinear analysis, studying some effects of damping using OpenSees PY.
Very important.
What's really cool about Shang's stuff is there's a lot of soil structure interaction stuff that we're accounting for.
Yeah.
Incorporating PYs.
So I'm also an affiliate professor at UW, and I'm also working with my advisors, my previous advisors as a PhD student, advising some master students at UW, and we have a student looking at trying to model bridge columns or bridges in Washington State, trying to capture the soil structure interaction, trying to capture, you know, the abutments and all that stuff. And so maybe at some point we should set up a meeting separately with you and just talk about, you know, some of the, I know that Max sent us a lot of his previous codes that he developed for modeling bridges, and we're going to try to use that and sort of build up on it and try to model some Washington State bridges. So maybe there's some room for,
Sure.
you know, collaboration. Yeah.
Thank you very much.
Yeah, no problem. Who else? Subicha.
Hi, I'm Subiksha. So I'm a master's student here at the University of Auckland. I'm doing my master's, which is like research-based, and I'm using OpenSees. So for me, both Python and OpenSees and mostly the coding stuff, whole thing is new. And so I'm modeling a breeze that is 1 kilometer, almost a kilometer, I think more than a kilometer long. And it's being demolished. So my supervisor team and Max and we all are having several researches going on that breeze. So I'm making an elastic model for the breeze, and we had some sensor data from the field that I'm going to compare and determine the parameters that will be controlling the behavior of the breeze. So basically it's elastic model for now.
Oh, cool. I mean, that's how you start every model, all elastic, and then you slowly make it more complicated, one change at a time, check to see the results, make sure it makes sense. And I mean, that's how we all started. Even today, if I'm creating a model from scratch, it's usually this all elastic, everything is fixed, and then you slowly release things and make it more complicated with time. Okay, so so I guess I'm gonna start sharing my screen. Is that okay, Max?
Yeah, go ahead. Yeah, I enabled it. And again,
and so
jump in as he goes, guys, if you have questions. So
yeah, please don't. Yeah, I mean, just feel free to interrupt at any time. If anything's unclear, let me know. The first couple of slides I'll talk. So today's presentation is gonna be about the effects of simulated magnitude 9 earthquake on reinforced concrete wall structures in the Pacific Northwest. So I'll start off by just giving you guys some background information just so that you know what the motivation is for this research. So the seismic hazard, like New Zealand in the Puget Sound region, includes large magnitude earthquakes due to the Cascadia subduction zone. And this type of earthquake, let me get my laser pointer on. Okay. So this type of earthquake has about a 500-year return period. The last one was around the 1700s. And so the USGS estimates that there is a 10% chance of this large magnitude earthquake happening in the next 50 years. Motions during large magnitude earthquakes, as many of you may know, is that they're long in duration. And the effective duration is currently not considered in design codes in the US. On top of that, Seattle and many areas in the Puget Sound region are built on these large sedimentary basins that are known to amplify ground shaking intensity. And this effect could affect structures, and yet it's not considered in current design codes. We also don't have any recordings for this type of earthquake. Unlike New Zealand, the seismicity in the Puget Sound or the Pacific Northwest has been very quiet. And so we don't have we don't have recordings of this earthquake. And so its effects are kind of poorly understood. And so I'll start off my talk by discussing some of how we address the paucity of recordings in the Pacific Northwest using physics-based simulations. This is something that is sort of new in the area of seismology and is getting a lot of attention. And so I'll talk about that a little bit. I'll talk about some of the characteristics of the ground motions that are produced from physics-based simulations, in particular physics-based simulations of magnitude 9 earthquakes. And then towards the last half of the talk, I'll take these motions, I'll subject them to structures in OpenSees, and then I'll talk about how our buildings perform And then at the very end, I'll talk about some of the strategies that engineers could do or take so that you reduce collapse risk. So before I begin, I just want to say that, you know, a lot of the work that you see here is not just me. It's really, when I did my PhD, and all this work was done during my PhD. When I did my PhD, I was on the SEDIMENTARY project that had researchers from all fields, many different agencies. And so I just want to just acknowledge that this is a group effort. I'll start off by saying that there was a lot of funding agencies that made this research possible: NSF, the USGS, ERI, and ATC. A lot of the computational resources that we use to make this research happen, whether it's physics-based simulations or OpenSees modeling, was all done in DesignSafe. I do encourage a lot of my students, and I think people in New Zealand do have access to DesignSafe, so I would encourage people to use DesignSafe to solve any numerical problems that they have. And lastly, you know, I want to acknowledge the M9 project team. So the physics-based simulations that were created for the M9 magnitude 9 earthquake was headed by a team of seismologists in the United States Geological Survey. This team was Art Frankel and Aaron Worth, and they started off by picking out 30, because you don't know what the next magnitude 9 is going to be. So what you try to do is you simulate 30 stochastic simulations of all possible magnitude 9 events. And so they did this by choosing 30 simulations, and within each simulation, they varied lots of parameters. You can think, I mean, a structural engineer, when he varies parameters in structural engineering, they could be concrete strength, design, you know, the strength of the column, the height of the column. In a seismologist sense, they would vary parameters like hypocenter, like the sequencing of the rupture, like the depth of the rupture, the velocity of the rupture. So these are all parameters that people are uncertain about. But the way to capture uncertainty is you just vary all of these parameters differently, randomly, and create, you know, we chose 30 simulations. You could create more if you had more computational power, but we chose 30. And so depending on, so what they did next was they picked out 30 realizations that they wanted to test. They used seismic wave velocity models of the Pacific Northwest region that included deep sedimentary basins. Then they used high performance computers and finite difference simulations to generate motions across a 1x1 kilometer grid across the Pacific Northwest. So for each location, you have a time history. They then supplemented those time histories that they generated deterministically using ground motions that have high frequency. And the reason they did this is because you can't simulate a ground motion at all wave bands because it takes a lot of computational power. So what you do is you simulate the longer period stuff, which takes less computational power, and then you supplement the short period bands using just random stochastically generated energy waves. And so you combine the two and you get a ground motion that you could use. So here's, yeah.
What's the computational power? Do you mean the processing power of the software to model it?
So one of these runs typically takes about, I think it was like 20 like 86 cores. It would take it 8 hours. When we first started the project, it would take like 4 days to run one run, but then computational power increases with time. And so by the end of the project, or halfway into the project, the runs were taking like 8 hours to complete. But then once you complete a run, there's a lot of post-processing that's required, and the post-processing typically takes another day or two of computational resources. And so you're looking at, you know, thousands, like it wouldn't be possible. We couldn't use any of the local clusters at the University of Washington. We have to use DesignSafe, which uses Stampede, and that there's like thousands of, I think 64 processor nodes there. And then we used some of the Department of Defense's clusters because this project is funded by the federal government, and because our employees of the USGS, they were able to convince the Department of Energy in the US to give them computational resources. So we use some of that as well. Yeah.
So Nasser,
Okay.
are these ground motions available anywhere?
They are, yeah. So all these motions are available. There's two ways to get the motions. You could get the motions from Design Safe. You could also get the motions on a website that's hosted by UW, where you would put in like the lat lon or the station name that you're interested in, and it would give you 30 the simulated 30 runs for a magnitude 9 earthquake for that location.
Sweet.
And I can share that information with you later.
Yeah, that'd be great. So for anybody who's doing research on long duration ground motions, this would be a good resource to get some of those ground motions. So
yeah, definitely. So here's two examples of two realizations that we ran from the 30. And the first realization, so these are animations, and what you'll see coming out vertically from the ground is the time histories. So realization 1 is rupture towards Seattle with a hypocenter just off the coast of Washington. Realization 2 has a hypocenter just off the coast of Oregon, rupturing away from Seattle. And so the thing to notice about this is that both of these simulations are a magnitude 9 earthquake, yet realization 1, if you look at for Seattle, the time history is quite different from this realization. Both are a magnitude 9 earthquake. So if one were to happen tomorrow, it could be either this or this. And the differences that we're seeing between the two realizations is attributed to the differences in rupture parameters that are taken between the 30 realizations. And so here's the velocity time history for the realization 1 and velocity time history for realization 2. And what you start to notice is that there are differences in the amplitude. If you look a little closer in like the spacing of the wiggles, you'll start to see that that means that there are differences in frequency content between the two realizations. Now, the nice thing about this is that structural engineers have figured out a way to quantify both amplitude and frequency content using a response spectra to sort of infer what the demands would be on a structure. And so here's a response spectra plotting where I plot spectral acceleration versus period for the two realizations, where this is the realization rupturing towards Seattle, and this is the realization rupturing away from Seattle. Now, both are a magnitude 9 earthquake. Now, if you had a structure, say at 2 seconds, say a 20-story structure, 2 seconds, and say that structure had a strength that corresponded to 50% of its weight, okay? Now, in realization rupturing towards Seattle, that structure would yield and deform inelastically. Whereas let me get my pen, one second. So this is my structure. This is what my strength is. So in this realization, it's going to deform and yield inelastically. But under this realization, the structure is going to move around and it's going to deform elastically, but then after the earthquake is over, it's going to return back to its original place. And so both are a magnitude 9 earthquake, but there's a lot of variability in the response. And so fortunately, we ran 30 simulations and so that we could understand the effects of a magnitude 9 event probabilistically. And what we saw is that the spread is quite a lot. It is quite a lot. Where you have, a lot, and like, so if you compare this to the design spectrum, so the red line here is what structures are designed to in Seattle. You'll start to see that a big portion of the motions sort of exceed the design spectrum, whereas there are some that are less than the design spectrum. In fact, I think 20 out of the 30 at 2 seconds, so a 20-story building, 2 seconds, 20 out of the 30 would be enough to yield the structure if it was designed to this intensity. Now, another interesting thing that we saw is that if you went about 80 kilometers south of Seattle, but you were still at the same distance away from the fault rupture, we saw differences in shaking intensity, where the amplitude of the shaking reduced. And if we were to quantify this using the response spectra, we saw that at 80 seconds south of Seattle, the motions, the spectral accelerations of the motions were actually quite lower than the design spectra. And we were like, well, what could this be attributed to? And so we know, if you remember from my first slide, we know that Seattle is sitting on the deep sedimentary basin. And so we think that the differences that we're seeing regionally between Seattle and so other locations is attributed to the basin. So for those of you that don't know what a basin is, so in Seattle, what we have is this glaciated sedimentary rock, where thousands of years ago, more than 1,000, the last ice age, there were these large ice sheets that were sitting on this sedimentary rock. And because of the weight of this ice sheets, it was heavy enough to sort of compact the soil layers, making it really stiff for buildings to be founded on. But the stiffness of this sedimentary rock is still much smaller than the surrounding mountains, which is the Olympics and the Cascades. And so that's important, because when you have seismic waves traveling from the fault rupture plain all the way to Seattle, once they hit the sedimentary basin, they're going to amplify in ground shaking intensity. And the first type of amplification that's going to happen, they're going to amplify in three ways. The first type of amplification that's going to happen is the differences in impedance contrast. The second type of amplification that's going to happen is conversions of waves at the surface from shear waves to surface waves. And then the last type of amplification that's going to happen is due to the lens-like shape of the basin, where it's going to start focusing energy or focusing the waves to certain points of around in the basin. And so how do we measure for this? So how do we know that we're on a basin? One way to do that is to look at the depth from the surface. So let's imagine, this is where our building is. And so we take the depth from the surface where that building is founded on, all the way to rock with at least 2.5 kilometer per second shear wave velocity. So that's like kind of stiff rock. So if you're in the deepest part of the basin, you'd expect this distance from the surface to very stiff rock to be quite large. And if you're in like the shallowest parts of the basin or outside of the basin, you would expect this distance from the surface to stiff rock to be much lower. And so if I calculate this parameter regionally and plot this, you get this, where I'm showing Z2.5, which is the depth to rock. And in Seattle, the depth is around 6 kilometers. Whereas if you go to La Grande, which is that place that was 80 kilometers south of Seattle, that distance is around like less than 1 kilometer. And so we know that this location is in the basin and this location is not in a basin. And so the difference that we're seeing in shaking intensity is mainly attributed to this basin. We can also see this if we plot spectral acceleration at 0.5 seconds and spectral acceleration at 2 seconds. We start to see at very long periods where the basin is expected to amplify shaking intensity. We can start to see that if you're in a basin, you get higher amplitudes of spectral acceleration intensity. At shorter periods, this doesn't happen because the basin doesn't amplify short period accelerations. So that's one thing that we noticed from the simulations. One characteristic that we think is going to affect building response. Another characteristics that we thought was interesting and could affect building response is what I'm going to call spectral shape. Yeah.
Just to give a local context, so Wellington, for example, it kind of came out after the Kaikoura earthquake that Wellington is actually sitting on a basin itself. I don't think it's quite as large of a basin as the Seattle basin, but there's definitely, if you look at ground motion recordings from Wellington, you'll see the long period amplification. So that's what that's from if you're looking at ground motions recorded in Wellington.
Yeah, so so like in Wellington, for example, if you go to the downtown area or the area where the Science Museum is, I think that's like in one of the deepest part of the basin in Wellington. Whereas as soon as you start going uphill, I don't know what it's called, but I've been to Wellington like once in my life. But if you start going uphill, that's where you start getting into like stiffer and stiffer rock, and you gradually move away from the basin. So imagine if you had two recordings, one on those hills and one like right in the downtown area, and you were to look at them during that earthquake, you'll see large differences in shaking intensity, and those differences are really attributed to what's underlying. You know, the basin is taking these waves and it's sort of suppressing certain frequencies and enhancing other frequencies. Turns out those frequencies that it enhance happen to resonate with taller structures. So you'll see you'll see shorter buildings on a basin being sort of protected, but you'll see taller buildings on a basin sort of being shaken more, and you're like, what's going on? It's really attributed to the shift in frequency content. So the second characteristic that I want to talk about is spectral shape. And what I mean by spectral shape is that if you have a building and you shake it and you start to see damage forming in that building, well, the fundamental period of that building starts to shift because it deforms inelastically. You get cracks, you get deformations in the concrete or the steel. And what that does is the period of the structure starts to elongate. When the period of the structure starts to elongate, what happens is the waves at longer periods start to matter more than the waves at shorter periods. And so we can see this here, where you have this structure towards Seattle, and you have this large, long period wave energy in one realization, and we don't have it in this other realization. And so imagine if we had a structure at like 0.5 seconds. And let's say that under these two cases, that structure yielded, and it would to deform inelastically. The minute this structure yields and starts to see this much energy at longer periods, it's gonna affect the performance, or it's gonna yield the structure and have it deform more than if the spectral energy were to reduce with period. So I would imagine that I would see that this realization actually, as the structure deforms, it saw less and less energy going in versus something like this. And so what I've done, part of my PhD, is I've figured out a way to quantify this. And one way to quantify it is to basically take the response spectrum that we have, and we were to integrate this. Let's integrate this and basically divide out this area, this integral, by the shape of the response spectra that assumes that it doesn't change. And so what this really means is that if I have a shape that looks like this, I'm going to get a spectral shape parameter or intensity that's less than 1. And if I have a response spectra that looks like this or like that, or something that just increases with spectral acceleration as with longer period, I'm going to get a value that's more than 1. And so if I compute these two, this intensity measure, SSA, spectral shape intensity measure, if I compute this for all the ground motions that I'm producing from the MM simulations, and I plot it with respect to period, and so here I'm showing spectral acceleration, spectral shape with respect to period. And what I've done is I've calculated this for different locations along the basin, where so the solid line is areas in the deepest part of the basin, and the dashed line is areas with the shallowest part of the basin. What I found is that if you looked at the spectral shapes were on average more intense or more damaging as you went from locations outside of the basin to locations inside of the basin. So we're going to see more damage for buildings inside of the basin because the spectral shapes are more damaging and the spectral accelerations are larger. And so I can see this again with on a contour plot. So here's just a map of spectral acceleration of spectral shape, and what we see is that if you're in the basin, which which is this area right here, you tend to get larger spectral shape intensity than if you're outside the basin. The nice thing about, so because there's like a hump at I think I have an image, because I have a hump at say 2 seconds, if my structure is at 2 seconds or 1.5 seconds and it yields, it's actually going to go past the hump. So 2 seconds. So if you were to compute SA at 2 seconds, you generally saw less spectral shape or spectral shape intensity than at 0.5 seconds, where you're just before the hump, and if you yield, you're going to go through a hump. So this is something else to consider. So really tall structures, the spectral shapes might be not that damaging. But if you say you had a 1 second structure and you were just before the hump and you're going through a hump in the response spectral shape, you would expect more damage under that ground motion. So another thing that I talked about in my first slide is that large magnitude earthquakes are long in duration. And so here's just the time history for these two realizations for Seattle. And they're about 6 seconds long from end to end. They have a significant duration, which is another ground motion intensity measure for duration, of about 120 seconds. If you were to compare this with like a crustal earthquake, so let's say Northridge, I mean, it's like an order of magnitude longer. So when you have long motions that are this long, you would expect them to go through more, you'd expect them to be longer in duration. So you'd expect the structure to go through more cycles, and you'd expect the structure to accumulate more damage. And so that's another characteristics that I want you guys to be aware of. So thus far, I've showed that the M9 motions have high spectral acceleration, damaging spectral shapes, and long duration. The next question that I want to answer is, what does this mean for spectral response? How are buildings gonna behave? And so to answer this question, we first wanted to see, well, what kind of building should we test? And so when we did this, I was like, well, let's go back to Seattle. Let's see what's being built in Seattle today. And so I looked at the building stock for most of the tall structures in Seattle. And what I noticed is that in the last 10 years, so here's height on the y-axis and year completed on the x-axis. And if you look at the last 10 years, the buildings that are being constructed mainly are just concrete buildings. So buildings that have concrete cores, kind of like this. And some of them have steel gravity systems. Some of them have concrete gravity systems. And so the buildings that we were gonna test using these motions would have these properties. So to design building archetypes to test under an M9 earthquake, we didn't want to do it alone. We wanted some buy-in from the community. And so what we did first was we approached all the engineers that were practicing in the city of Seattle, all the structural engineers. We talked to the city of Seattle and the city of Bellevue, which is just close to Seattle, and we talked to some geotechs, and we try to basically work with them to design a suite of archetypical buildings to design and build models for, and then subject to the M9 motions. And so when we did this, we came up with something like this. So we wanted to look at a range of buildings with a range of story heights, just because the motions that were produced from the M9 motion, some of them had damaging spectral shapes but low spectral acceleration. Some of them had long large spectral accelerations at longer periods. And so we wanted to look at a range of building periods. And so we did this by designing archetypes with a range of number of stories. We fixed the floor-to-floor height to about 10 feet, which is representative of sort of condo buildings. And we fixed the floor plate to about 100 by 100 feet. And we used a concrete core system similar to the picture that I showed before. And after looking through a couple of drawings and consulting with some engineers, we noticed that this type of structural system is uncoupled in one direction and coupled in the other direction. And the reason they couple it in the other direction is because they need to provide openings to access the elevator shafts. And the elevator shafts are typically in here, so right in the core. And we assumed that the buildings had basement levels depending on the height. So for a 4-story building, it had 2 basement levels, and it can go up to 4 basement levels for archetypes with 12 stories and higher. And so for every archetype, we designed it to modern codes, and then we built numerical models in OpenSees. And so I used actually, at the time, OpenSees Pi didn't come out, so I used actually Tickle OpenSees. But you can repeat this entire process again using OpenSees Pi, and the results will probably be the same. So this is just a schematic of the numerical model that I built in OpenSees. We used displacement-based elements to model the response of the core. There were about 6 displacement-based elements per story, each with 5 integration points. We modeled the gravity. I didn't model the gravity system explicitly. Instead, I modeled the gravity system using elastic beam column elements. And I put vertical loads on these elastic beam column elements just to, whenever the building sways, you get some overturning as a result that is funneled back into the core wall. I modeled the basement walls using an elastic beam column element. And we modeled the diaphragms using an elastic shear spring. So each of the integration points for the displacement beam column elements used modeled the concrete shape as an I shape, and we only looked at the uncoupled direction. So one thing that I studied is the uncoupled direction of the walls, and so I was able to idealize the behavior using this I shape. So if you take this and you basically just, that's what I did. It just simplified the entire process, and this is the shape of the core that I analyzed.
So Nasser,
this is what it looked like.
Why did you use displacement-based elements?
So so the convergence of displacement-based elements tends to be better in OpenSees than force-based elements. I started off using force-based elements, but then I couldn't get the models to converge, no matter how many iterations I forced each force-based elements to go through. And so what I realized is that if you wanted to have all your analyses converge under strong shaking, you achieve this in a better way with displacement-based elements. So then I have a paper that talks about, a modeling methodology using only displacement-based elements for concrete coral buildings. And so we use tests and stuff to basically come up with this methodology using displacement-based elements. But the main reason for using displacement-based elements is just the convergence. It was better.
Cool.
Not a good reason, but I couldn't, you'd have to dig into the force-based elements methodology and try to tweak the OpenSees code to converge during strong shaking, which is a dissertation by itself.
Yeah, no, I think that's a really good reason, actually. So
yeah. Yeah.
Also, Professor Max, I think even in Pawan sir has shown why displacement based would be better. Not only just the convergence, but also sometimes the endpoint results don't make very sense.
Yep, exactly.
Yeah, I think in force-based elements, you got some discontinuities and because it's trying to, it doesn't care about the displacement field, it cares more about the force field along the element, and so you got some discontinuities along the way.
In displacement.
But if you do displacement-based elements, one thing that you have to note versus force-based element, you can have one force-based element between stories. In displacement-based elements, you have to discretize the elements. So that's why I'm using 6 per story. You have to discretize the elements small enough so that you can get the response to be reasonable. So that's one thing that we noticed as well.
Because constant curvature, right? Constant curvature.
Yeah.
Displacement-based. So how did you come up with 6?
Honestly, I went back to the experiments. I modeled the experiments using 1 element, 2 elements, 3 elements, 6 elements, and I realized that 6 elements you match the experimental results the best.
Cool.
And so then I came up with a methodology of using if you used 6 elements per story height, you got reasonable results that way. And so that's what it's not a good enough reason, but it's just,
No.
I mean, you could go up to 12, 20. The more that you pick, the better, I guess. The slower your models are going to be, but the better the results. But I saw a point of diminishing returns after 6, so I just chose 6.
And then I guess one last thing before we leave this slide, does everybody understand, and the only reason I'm bringing this up is because in my nonlinear class last term, there were some people that hadn't seen this before. Does everybody understand what the leaning column is doing? Does anybody have?
Yeah, don't know.
For P delta effect.
P delta effects, yeah. So you have to, if you don't have a leaning column and you don't model your gravity system, you're basically not accounting for all the vertical loads on the gravity system that create moment at every story when the building starts to lean one way or the other. And so it's not conservative. It's not a conservative modeling approach if you don't include a leaning column to account for the P delta effects.
Yeah, very important if you're not modeling the gravity system explicitly.
Yeah. I think one way to improve this model is to start to model the gravity system, and introducing a sort of a moment spring right here, connect it to the wall, connect it to this column, and sort of model the contribute, because the gravity system in an earthquake does contribute to the resistance of the building to an earthquake, and so you want to include that here. So each integration point takes us, and so this is the fiber section that I used. There's concrete fibers to simulate the concrete response. There's steel fibers to simulate their steel response. In the next slide, I'll talk about what kind of material models I used for these 2 fibers.
Nasser,
So
sorry,
for concrete,
just a question.
Yeah.
Just to clarify, with your previous model, so you did not, so all the gravity elements were lumped together in the leaning column. Is that what you were saying?
So there was only one vertical line element that represented the axial load on all the gravity columns.
Right. Okay. Yeah. Cool. Thank you.
Because you're not modeling the flexural response or the response of that column due to the earthquake, the contribution of the strength of that column due to the building, it doesn't matter if you lump them all together or don't. It's just you just want so the axial load in this element right here better sum up to all the gravity load in all your columns.
Yep.
So,
Gotcha. Oh, I see. So what I was doing with my what I'm doing with my model is kind of like this actually, although I'm doing a dual system and then I'm modeling it in 2D. So I've got I don't have it yet, but I'm going to do it. I'm going to have a displacement-based core wall, and then I'm going to attach it to some steel frames, and then I'm going to have another leaning column for the to account for the 3D-ness of it.
Yeah.
And yeah, that's why that's why I was asking to clarify this one. So yeah, that makes sense to me.
Yeah. No, it's a very quick and dirty way to account for P delta effects. If you wanted to improve this, you would probably model your gravity system explicitly and account for the contribution of strength from the slab column connections.
Right.
And so that would be one way. So next, I'm going to talk about what material models I use in the concrete and steel. And so in concrete, I use concrete 02. But, and let's see if I can explain. I usually, like in typical presentations that I give people, I just go, like this is a 30-second slide, but I want to talk more about it. Because I didn't use concrete 02 per se. I modified concrete 02 so that you can specify the initial stiffness. Because concrete 02, you just give it this point, that point, and I think that's it.
Yep.
But I wanted to control the slope of the like sort of like the elastic stiffness of the concrete. And so what I did was I stole some of the functionality in Concrete 04 that uses Popovich's curve and implemented it in Concrete 02. Because I did this because I wanted to get the period of the structure because I wanted the period of the structure to be right. I wanted the period of the structure to be the inelastic, the undeformed, the uncracked concrete stiffness. So that's what I did. Because if you use Concrete 02, you didn't have control over the initial stiffness. So the periods that you're getting, if you use Concrete 02, you didn't know what they were.
So why
couldn't
didn't you just use Concrete 04?
Because, why didn't I use, that's a good question. I didn't use Concrete 04 because what's the difference between Concrete 02? Well, I think it has something to do with the post-peak stiff, the post-peak, Concrete 04 didn't, what did you, well, first of all, it's because I already calibrated Concrete 02 to experiments and it worked and it converges. And I think it has something to do, I can't remember the exact reason, but I think it has something to do with the post-peak response. So the response past this point was different between Concrete 02 and Concrete 04.
Yeah.
And I wanted to make sure the post-peak response was the same because I use a modeling methodology where I take this energy, which I call the crushing energy, and I regularize it. Yeah. And I talk more about this in this paper and this paper. Okay, well, let me just get over this point first. So for confined concrete, I used you can either use Mander, 1994, or you can use Satasiglu and Rasvi, 1992, and I use that because the differences between the two aren't really that much, but I just use Satasiglu and Rasvi to come up with the confined concrete capacity. But post-peak, I used a regularized approach so that you didn't get any mesh dependencies in your response. And that is talked about in more detail in Marafi et al. 2019. I should have probably, now that I think about it, maybe the presentation that I give should have been about that paper and not this paper. But anyways, we can talk about that later. I can come back for this paper. I can present this paper.
This is actually really important. The regularization is actually really, really important to eliminate your mesh dependencies when you have concrete failure. So everybody look into this who's modeling concrete.
Yeah, so this is something to test when you're modeling concrete. And this is what I mean by mesh dependence. Run your model, calculate, take your output, plot it. Go back to your code and double or reduce the mesh size by a half. So if you were using 2 elements per story, use 4 or use 8, and then rerun your analysis code. And what you'll see is that if you're shaking your structure using an intense ground motion, you'll see that the response of your concrete is different between the two models. And all you changed was just mesh size. And so to reduce this difference between analyses, to eliminate or to reduce mesh dependence, you have to regularize your concrete. And this is what I mean by regularized concrete. And so if you read this paper, I'll walk you through the procedure on how to regularize your post-peak stiffness. Essentially, it's just you're calculating the area, this red area that I'm highlighting right here, and you're trying to figure out how much area there is, how much crushing energy there is, and you're just making sure it's constant between mesh size. So I point you to that paper for more detail.
Yeah, if you send me that, I can we'll post it somewhere because this is really important, guys. Definitely, you should look into this.
Yeah, I'll send it to you.
Yeah.
The other thing that we did was so this approach that I'm following, we wanted to make sure that it was good. And so to test that it's good, usually most people go back to experiments. And so what we did is I modeled about, I think about 20 tests, I think. And we made sure that our model and the experiment matched. They didn't just match in this region, but they also matched in this region. And so because, we wanted to make sure that the deformation at significant strength loss between the experiment and the analytical model was close enough, because when this point happens, that's typically when building collapse happens. And so if you care about collapse, and a lot of building codes care about collapse, you have to make sure that your model can simulate significant strength loss. So that was one of the reasons why we chose displacement-based elements, because in displacement-based elements, you could go to this point. In force-based elements, your model would stop converging right about here, and you can't go there. You can't simulate that. You'll just get a non-convergence failure, and that doesn't really mean anything.
Well, so something I'll bring up, Nasser, now that you say that, if you guys read papers about people that model collapse, a lot of times what they'll do is they'll say non-convergence equals collapse, okay? And that is not, you should not be doing that. So when you're digging into papers where they run IDAs and they're looking at collapse probabilities, if they start saying non-convergence equals collapse, you should start thinking, questioning a little bit about what they're doing, so.
Yeah. I mean, it's a very conservative assumption to assume that the building collapsed as soon as your numerical model doesn't converge is a very conservative assumption. And so some engineers and some researchers would tell you that I can probably get another, 2-3 cycles after that building, and that's typically enough to save the building from collapse. And so so that's something to look into. I mean, ideally, we would want to be able to simulate all the way to collapse. But for certain software, certain codes, sometimes it can become a challenge.
So my second question here, Nasser, I'm assuming that all of these experiments that you validated your model to were flexure dominated because you're running a flexure.
Yeah. So that's another thing. So most modern concrete buildings are flexure controlled. If I decided to look at, say, older structures that had more squat walls, and they were shear controlled, then you would have to use a modeling methodology that takes into account the inelastic shear response of the wall. And that was something that I avoided because the walls that I studied were all flexure controlled. So something to think about. If you're interested in the squat walls, then you'd have to use another modeling methodology. I actually just reviewed a paper where they used LS-DYNA, not OpenSees, LS-DYNA, and they used a shear flexure controlled element. And so that's sort of the best of both worlds. You can model flexural controlled walls, and you can model shear controlled walls using that modeling methodology. Something to look into.
Do you have any experience with the MVLEM?
Well, so I know Christian Kalsvari. I've talked to him a couple of times. Based on the papers that I've read from him, it seems promising. Although I have heard from him that you do get some non-convergence sometimes, and I don't know if he has looked into it or if he's worked, if he solved those problems, but there could be some so one, his models take a lot longer to run. Two, there's going to be more non-convergence collapse.
Just so everybody's clear, the MVLEM models, it's a combined, it takes into account shear deformation and flexure in OpenSees. So it's something you can look at. Yeah. Sorry, go ahead.
So at really large strains, what I've done is I've modeled, so I take this point as like, that's when the concrete spalls, and this value is determined based on the crushing energy, so the area of this right here. And so once the concrete spalls, I use a constant sort of residual strength, which is about 20% of F prime CC or F prime C. And actually, this is an assumption that I take. I don't think we have a lot of experimental data to back this value up. One things that I did find in this paper is that if you cared about collapse, and if you varied this from 0.2 to 0.3 or 0.1, you got different collapse values. And so one thing that experimentalists should do, and people who are doing experimental research here, is that sometimes we need to take our experiments past this point. We need to figure out what this number is. Most experiments stop before we get to this. So something to look at. For steel, I used the steel law 2, which is the Mitigato and Pinto stress strain relationship, and I lumped that in with a min-max wrapper to control the strains at which the steel fractured. And so in tension, I assumed that the steel fractured about 20%. In compression, I assumed that the steel buckled and fractured when the concrete spalled. So that's basically, if someone were to ask you what buckling model you're using, that's the buckling model that I'm using. There are more complicated buckling models, but this one I found to work well and to give robust predictions of building response.
So
Another thing that I did, yeah.
Go back to your, I like this model. It's nice and simple, and I'm assuming it converges pretty well.
Yeah.
With regards to the compression side, I can't remember how the min-max wrapper works. If it fails in compression, can it still carry tension?
No.
So it's just bar is
It
gone.
fails, it fails. Done. Bar has fractured.
Interesting. And so you were
The
able to accurately capture the cyclic response, even though, because in a real test, if you think about it, the bar buckles and then you go to the other direction, it'll open up and actually give you tension resistance. But you're able to
but then it'll fracture. It'll fracture right after. So once the bar buckles and then you stretch it out, yeah, it gives you some strength. But then as soon as you take it, it'll just fracture. Cool. So that's the assumption. It's not. It's so if I were to if say you ran some really nice experiment at University of Auckland of a shear wall test, and you told your student, go and model this, I wouldn't choose this modeling methodology. I would use I think Professor DeCall from University of Canterbury. He has a buckling model, more complicated, takes a long time to run, but you can at least capture that behavior, you know. But for what we're doing here, we're trying to figure out, like, on the bigger picture, the collapse risk of these walls in an M9 earthquake. If I was trying to simulate one experiment, I would probably make this modeling methodology more complicated. But if I wanted something that was quick and dirty, I would go with this.
Yeah, yeah. So that's an important point. When you guys are modeling, think about what your end objective is, right?
Yeah.
If you're going to actually model strain in the reinforcing bar as a function of deformation of the wall, you're not going to want to use this because it's not going to give you the right answer. But it gives you the right global answer, and that's what. So
always. Yeah. So you want to, in research, you could go down a rabbit hole every time you try to make stuff more and more and more and more complicated. If you wanted to use the state-of-the-art way of doing something on everything that you did, you're never going to finish. Your PhD is going to be a 10-year PhD. Sometimes you have to, you know, my approach, and I think Max's approach was that way during his PhD, is that we made our models complicated enough for people to believe us.
Yeah.
And then we always know how much more complicated we can make it, and always state that as a limitation of our work. Because when you go to a conference and you present your work, there's always going to be this person sitting in the back. He or she just developed this amazing modeling methodology that he or she wants people to use. And he's going to ask that question, he or she's going to ask that question, like, hey, did you ever think about this modeling methodology? You just have to acknowledge that model methodology is there. It's more complicated, it's there, but it's a limitation of the work. And given the computational resources and the time that you have, you did not look into it. And so something to just think about.
Yep.
So the next, because we were modeling long duration shaking, or we had long duration earthquakes, we wanted to make sure that we accounted for the degradation of the steel with cycles. And so if you use steel O2 straight out of the box from OpenSees, you couldn't do that. There are some material models out there that can degrade with cycles, but getting them to converge was a problem. And so what I did was I took steel O2 and I basically modified it to use Coffin-Manson and Miner's rule. And what that means is that after every cycle, I would figure out how much energy I spent, how many cycles I've gone through, and I would figure out what the, in this next coming cycle, what steel strength do I approach? And so what you see here is the difference between steel O2 and what I call steel O2 fatigue. And so the first cycle, the black line and the gray are right on top of each other. And so you go back. Now, here's the interesting thing. Once you get to this point, everything's the same. You start reloading again, or unloading and then reloading, you'll see that the two material models start to diverge, where this, and it doesn't happen, it's not, you can't really see it here that much, but the strength that your steel approaches is slightly lower than if you just use steel O2. And so if you cycle this back and forth, you start to see that the black line degrades more and more. So like steel O2 by itself doesn't degrade. So this is what the strength is. But if you use steel O2 fatigue, and you cycled your steel a lot, you saw degradation in strength. And that's what this essentially modification does. And the reason we had to do this again is because we had long duration shaking. So we wanted to capture the effects of steel fatigue. And we used Sashi Kunith from the University of California, Davis, to come up with some. So he ran all these bare bar tests and calibrated some of the Coffin-Manson and Miner's coefficients to take into account degradation. And so that's what I used for this. And so I would recommend people that are interested in long duration earthquakes, I recommend them to check out steel O2 fatigue. That is now in OpenSees, Tickle. I don't know if it's in OpenSees Pi.
What's it called?
We can, steel O2 fatigue.
Called steel O2 fatigue.
Yeah. So I would recommend people to check that out. So the next thing was, so we built OpenSees models for all the archetypes. We then subjected them to the M9 motions. We simulated damage, and then we compute probability of collapse. Now, before I start showing you all results, I want to acknowledge that I'm not simulating the gravity system, but I need to account for partial building collapse due to gravity system failure. So you have all these gravity system connections and they're going along for the ride, right? Even if your lateral system, your core wall can go to 5% drift, 6% drift, 7% drift, chances are the gravity system that's going along for the ride is probably going to fracture or rupture and break. And when that happens, your slabs are going to start to fall and you're going to get partial building collapse. And I have a good picture of this, but it's not in this presentation. It did happen after Northridge, where you saw partial building collapse because the gravity system couldn't go along for the ride. And so what I did was I needed to come up with a non-simulated collapse mechanism, which is failure of the gravity system connections. And to compute what this is, I looked at many tests that were compiled by Hust. I think she's from a university in Texas, and she compiled a lot of slab column tests, and she looked at what drift capacity these slab column tests had after many cycles and how they varied. And what she found is that the gravity system connection had more, was carrying more gravity load. The drift capacity reduced, which is what you would expect. There's less capacity reserved for earthquake deformation. And if you included shear reinforcement, the gravity system increased. So if you had shear reinforcement or stud rails or rebar or whatever, you could get more gravity, ductility capacity from your gravity system connections. And so what I did was, after talking to some engineers, they said, we always put shear reinforcement in our slab column connections. We always use shear studs because chances are these are PT slabs, post-tension slabs. And we like to keep our gravity shear capacity between 0.4 to 0.6. So then what I do is, okay, let's take all these points that fit this criteria, and let's try to figure out what the distribution is they have in drift capacity and come up with a fragility curve where I plot the probability of partial building collapse with respect to drift capacity. So then for every analysis that I run, I'm going to go and I'm going to figure out what the maximum drift that analysis saw. If it's 6%, then it has a 50% chance of collapse due to gravity system shear failure, gravity system failure.
So,
and so then,
take a step back here, Nasser. Is everybody clear what he means when he says simulated collapse versus non-simulated collapse? Does anybody need clarification on that? So can somebody tell me what his simulated collapse failure is in his model?
No, not me. You have to explain that.
Can you explain what you mean by simulated collapse versus non-simulated collapse?
So a simulated collapse mechanism is basically when you're running your, remember that P delta column that I had? And say if I run my model under a strong earthquake, and basically I shake my building, and at some point, what's going to happen is the moment capacity of my core wall is going to reduce as I shake the building more and more. And it's going to reduce to a point where the overturning moment of the gravity system is larger than the moment strength of the shear wall. And when that happens, your wall can no longer can stop your building from leaning over. And so what's going to happen is your model is going to deform a little more and deform a little more and deform a little more until you get this global P delta instability, meaning that your gravity system has created a P delta moment that cannot be resisted by your shear wall. So that is a simulated collapse.
So what he's saying is his model essentially is a cantilever fiber model that can capture axial and moment failure. Okay, and so when you subject that model to a ground motion, the simulated failure mode is going to be combined axial moment failure. You're going to develop a hinge at the base, let's say, and it's going to collapse, right? Yeah. His model can explicitly capture that behavior. So that's his simulated collapse mode. Now he's not explicitly modeling the gravity system or the floors. And so what he has to do is he has to check in his model when the drift exceeds 6%, let's say, in this, he's going to say, okay, even though my model hasn't collapsed, I haven't developed that hinge, I know that the floor has failed because I've developed this probability function for the floor system collapse. So even though his model hasn't collapsed, he says, okay, I've exceeded this drift in my model, so I've collapsed because of the floor failed. And so that's a non-simulated collapse mechanism. Does that make sense to everybody?
Yep. Yep.
Cool. And so you might do this also. I know that these walls are super slender, right? But you could do the same thing looking at shear. So even though his model doesn't explicitly capture shear, you could say, okay, have I exceeded the shear capacity of this wall at any point in the model? And if it's been exceeded, you say, okay, I failed back here. I've exceeded the shear capacity of the wall before I flexually failed. So that's simulated.
That is a non-simulated collapse mechanism. Although some researchers would tell you that shear failure does not necessarily constitute collapse.
True.
So if you were to say that and treat it as collapse, you could expect people to say, well, how do you know that shear failure is collapse? I've seen columns, I've seen walls fail in shear after Male, after many earthquakes, but the building's still standing.
Yep, good point.
Shear failure does not constitute collapse. And so some researchers have called that collapse, but some have called them out on it. So that's something also to take into account. So all good presentations have an animation. And so this is an animation about where I'm showing the response of the walls during a magnitude 9 earthquake. So here I'm gonna take my 12-story archetype and I'm gonna subject it to my M9 realization towards Seattle and my M9 realization away from Seattle. And what you'll start to see is that the contours in here represent the strain that's being seen in the concrete. And then these dots, these red dots that are here, just indicate the probability of failing the gravity system. And so between the two realizations, we noticed two things. We noticed that, so the dark gray that you see here in the animation represents the area where the strain has exceeded the yield strain of the steel. So the steel probably yielded in those areas. And so what you start to see is that under this realization, a lot of the steel has yielded. Whereas in this realization, only right here, we saw steel yield. In this realization, a lot of the gravity connections all have probabilities of failure that are more than 80%. So the drift that the rotation that these connections have gone exceed what would be 80% collapse. So if you go back to this fragility, they're basically somewhere, the rotations are more than, say, 6.5%. And then the last thing is, whereas here, we didn't see that. So all the probabilities of failures in the gravity system connections is less than 20%. So yeah.
Buildings are controlled by the gravity system, like the collapse response of these I mean, if I look at the one on the left here, it clearly didn't collapse, but it's exceeded the collapse for the gravity system. So so your non-simulated collapse mode is actually controlling.
There are, so yeah, the my non-simulated collapse mode controls a lot. There are some realizations that call the total P delta instability. But when you have a P delta instability, what happens is your drifts start to increase without bounds. And basically you would produce a probability of collapse of 100% of the gravity system. So so if you have a P delta instability, chances are you also have
that makes sense. Yeah.
A gravity system failure.
Yeah. Cool.
So the next step is I took the 30 simulations and I simulated the probability of collapse for all 30. And then I summed it up. And basically, where I assumed each realization has a 1 in 30% chance of it occurring. And so and I did this for all archetypes between 4 to 40 stories, 4 to 24 stories. And so what you see here is that under an M9, so if an M9 were to occur tomorrow, it would have a 20% chance of it occurring, a 20% chance of it causing building collapse for these archetypes. Now, interestingly, so this is a collapse probability conditioned on M9 occurring tomorrow. I could, to make sure that my buildings were properly designed, what I did was I said, let me select motions that represented the maximum considered earthquake. So the earthquake that you design buildings to. And I would to subject these earthquakes, these earthquakes that represented the maximum considered earthquake to this archetype and compute the conditional probability of collapse due to the maximum considered earthquake. We generally saw those numbers to be less than 10%. Now, why do I say 10%? Because the code says that if you had a reasonable building, if you designed a building with a reasonably low probability of collapse or risk to human life, it generally had a 10% chance of failing in the MC. And so these buildings that I designed had
right?
less than 10%.
I mean, FEMA.
No, because the new code, the new ASCE 7 code, tackles this issue in terms of risk, 50-year collapse risk.
I see. So P695.
So it targets, it targets a 1% chance of collapse in 50 years.
I see. So guys,
and that
the New Zealand code does it at all, just so that we're
so for people who are not thinking of moving outside of New Zealand, you can just ignore what I'm saying. It's all but just so the reason I'm showing this orange line is just to tell you guys that my archetypes are code compliant and they're good. Yep. Okay. And that under an M9, which has a 500-year return period, keep in mind the MCE has a 2,500-year return period, I'm getting 20% more chance of collapse than the MCE, what I think the maximum considered earthquake should be. And so the reason that we see this is because there are things missing in the MCE that need to be accounted for. And I'll talk about this in a couple of slides. So next, so this is where Max and I were talking about collapse risk versus collapse probability in the MCE. So the code quantifies building response in terms of risk to human life. And the way they do it is they calculate they say your building has to achieve at least a 1% chance of collapse in 50 years, considering all possible earthquake mechanisms that control a particular site. And so to be able to calculate that number, we have to select earthquakes or motions that represent an earthquake that I'm going to get in 50 years, in 100 years, in 500 years, in 1,000 years, in 2,500 years. And I need to select motions, so at different return periods, and I need to select motions considering all the different possible fault mechanisms or earthquake sources that my site could see, that my building could see. And so I do this using a multiple stripe analysis where I looked at like 5 intensity levels from a 100-year all the way to a 5,000 year. I looked at earthquakes from crustal sources, interslab sources, interface sources, and all the different source mechanism types. We also selected motions to represent the conditional mean spectra, which I'm not going to get into, but it's like so this is like trying to capture all possible earthquake motions that this building could be affected to. And so once you do that, we constructed these collapse fragility curves, which tell you what the collapse probability would be given return period. And then we took these curves and we integrated it with the annual rate of collapse or the hazard curves to basically calculate this final number, which is the annual rate of collapse. So what is my likelihood of collapse in 1 year? And then we can convert that easily to a 50-year collapse risk, because that's how the building conveys this information. And basically a bunch of number crunching, and what we get is a 50-year collapse risk. And what I told you guys is that 1% is the building target. So this is what I'm trying to target. Now, if I were to do this process where I would select motions to represent the earthquake hazard, but not consider basin effects, I generally, so what's being done today by the building codes, I generally saw a risk that's less than 1%. So that's good. My buildings are code compliant. But the minute I start to select motions with basin effects, I saw that my collapse risk would increase a lot. Similar to what I was seeing before in this plot right here. So the difference between this and this is just because this doesn't include basin effects, because the code right now doesn't include basin effects, but these include 3D basin effects, which cause those more damaging ground motion characteristics. So then I said, well, okay, great. This curve is all computed using empirical relationships. This curve was also computed using empirical recorded ground motions. How do I repeat this process but include some of the M9 simulations in this? And so what we did was we said, let's just use all the earthquake sources, for all the ground motions that are not associated with magnitude 9 earthquakes. Let's use recorded data because we have that. And for all magnitude 9 earthquakes, let's use the physics-based simulations. And for both, let's compute the annual rate of collapse. So for all large magnitude earthquakes, we'll use the physics-based simulations, and we'll compute annual rate of collapse. And for all other sources, we'll use what I've showed previously using recorded motions and compute the annual rate of collapse. We'll combine the two and we'll compute collapse risk. And what here you'll see is that once you included the simulations, you actually saw a much larger chance of collapse, about 2.6%. So the code targets 1%. We're seeing on average 2.6, about more than double what the code is seeing. And so the reasons for this is because the building code that we're using today uses a seismic hazard that doesn't include basin effects. And more interestingly, it doesn't include ground motions that we would expect from the Seattle basin. And so what can engineers do to reduce collapse risk? They can start off by increasing the design spectral acceleration so they can make their building stronger. And so if we were to repeat this entire process and say, what happens if we increase the building strength by 25%? What happens if we increase the building strength by 50%? And what we saw is that if you increase the building strength, you saw reduction in collapse risk. Great, so that's what we could do in the future. We could also do something else. Well, what if we don't increase design strength, but instead we make our building stiffer? And we make our building stiffer by designing it to a lower drift limit. So US codes target 2% drift limit. I don't know what New Zealand does, but I think so 2%. So if we reduce the 2% to say 1.5%, so we're targeting a lower drift limit, meaning that we need our core wall to be slightly stiffer. And if we did that, that also reduced collapse risk. Alternatively, we could also make the gravity system connections more ductile. And so if you remember that non-simulated collapse, you remember that fragility curve that I had, it went something like this. What if I, made my gravity system a little slightly more ductile and we pushed out that curve? And so the more we push out that curve, the the lower it reduces the collapse risk. And so that answers your question, Max, of does the gravity system connections control collapse? And you'll see that it does, actually. You know, if you pushed your collapse fragility for the gravity connections towards the right, you'll reduce the collapse risk.
Nasir, one question.
Yeah.
I think the previous, this slide, few things are very contradictory. If you have restrictions or high restrictions on drift limit, you immediately reduce the ductility. And also, I'm not quite sure how is strength and drift or stiffness different.
So, okay, so your building can still go through similar swings. So it could go through similar
Cycles,
deformations, but you could add more steel in your concrete, and that would generally save
strength.
the building from collapsing. That's one approach. You could say, I don't want to add more steel. In fact, I want to reduce the amount of steel, but I want to add more concrete in my core. I want to make my cores bigger, thicker.
So stiffer.
Basically, what that does is that increases stiffness. And actually, that also does something else. It reduces the drifts the building goes through under that earthquake, hence saving the gravity system from going through large deformations. And then the last approach is say, well, what if I don't do anything to my core wall? What if I just make my gravity system more ductile? What if instead of having
high steel, low steel?
What if I pinned, for example, my connection from the column to the slab? If I figured out some innovative way to connect a PT slab to a concrete column using a pin connection, okay? And if I did that, that actually reduced my collapse risk because it sort of saved my gravity system from partial building failure. Does that make sense?
Yeah, absolutely.
Yeah. And so in reality, I don't think, as a researcher, I don't like to tell engineers what to do, but I can imagine engineers doing a little bit of each one of these. I can imagine the next code saying, we're designing for too little design strength in Seattle. Let's increase that by 25%. I can imagine the building code saying, oh, let's try to target lower design drifts. And then I could say, well, if you take a 25% increase in design strength and you use 1.75 drift capacity, the drift limit, and you maintain that 6% drift capacity of the gravity columns at 50% collapse, you generally got a 1% probability of collapse. And so that's like the takeaway, is that really going like into the future, we need to spend, like, making your building stiffer is not the only answer. Making your building stronger is not the only answer. It's a combination of that and coming up with more innovative connection types that can go through a large drift. And you see that happening. Like, I think I was in, and you see it a lot in New Zealand, really. Like, I was in, I think in one of the Nelson's airport in South Island. Like, they had some pretty nice connections of the timber to the roof, and you could see, like, okay, that building can go through large drifts before starting to see collapse. And so these are the kind of approaches that we tell engineers to take, is that how do we come up with solutions that are more ductile without necessarily increasing the cost of the structure that much. So this is my conclusion slide. Yeah.
Yeah, sorry, just to add,
Go
actually,
ahead.
after the Canterbury earthquakes, engineers decided to reduce the drift limit on their own, even without, government legislation. So now they're reduced it to 1.5%.
Yeah.
And it's actually
and
pretty
in fact,
common.
interesting that you say that, because after talking to a bunch of engineers in Seattle, whenever they design a really tall structure, Usually tall buildings in Seattle that are taller than 240 feet, they go through a enhanced design check, a performance-based design check. So engineers at that point need to do nonlinear models. They need to show that their structure has significantly low collapse probability. And so one way they found to achieve this is by designing your building to lower drift limits when you're doing your code prescriptive approaches. So if you designed up to that 2% limit and you went in and you evaluated your building using performance-based design, you generally saw bad performance. So what they found is that if you designed it to 1.5%, I don't know how they must have read some of the papers from New Zealand, but then they realized that if you designed it 1.5%, that's what I found too, is that you generally got reasonable collapse probabilities.
Cool.
So I want to conclude by saying that the MNI motions, there's a lot of damaging characteristics in them. They have large spectral fluctuations, damaging spectral shapes, and long duration. This definitely resulted in large collapse risk in the buildings that I analyzed. These buildings, if you analyze them using ground motions that they were designed to, you generally saw good performance, less than 1%. If you didn't include for basins, again, it's less than 1%. If you included basin effects, that collapse risk increased to 1.9%. And then if you included the MN simulations that are fundamentally different than the ones that are used in codes today, you got up to 2.6%. And so these collapse risks, while are more than the collapse target of 1%, you could reduce them by either increasing strength, increasing stiffness, or increasing gravity system drift capacity. And so with that, I'd like to conclude, and I'd welcome any more questions that you may have.
Thank you very much, Nasser. That was very, very interesting.
Yeah, no problem. I know we went a little over, but I for some reason, I decided to put more stuff and have it become more of a discussion. So I apologize for going over.
No, I thought it was a really interesting discussion. Does anybody have any questions? So I think some of the highlights of the presentation and something where I'll have Nasser send me some papers, and again, this video will be posted. But in terms of regularizing your concrete, I think that's something that's really important. And then another thing that I think some of you guys might be interested in is developing fragility functions. And so he talked briefly about multiple stripe analysis. I think there's one slide. We don't really have time to go into how to perform a multiple stripe analysis, but you have a pretty good paper on that, Nasser. So maybe we'll distribute that also for everybody. So yeah, does anybody, if there's no outstanding questions, I guess I'll just do some bookkeeping here at the end. So just a second, does anybody have any questions or no?
Just one question again, Nasir.
Got to say hello from the field. Hello from the field.
Oh, hey. Coming into our meeting. Cool. Sorry, there's a real question. Go ahead, Dinesh.
I want an important one, but on a personal side, so does your PhD or study deal directly with the data collection, as you had specified many times that it's a basin effect that created many differences and the variation of output of responses? Or is it mostly just the computational modeling part that you have focused on in the past years?
So my dissertation, we knew going in that basin effects were not going to make building response results look good. And so I remember, like, after my second year, I think this was like when Max was finishing up, I went to a bunch of engineers and I showed them this. I showed them this plot right here. And they saw that and they were like, we don't believe you. You're telling me we're not doing what we've been doing for the last 20 years.
It's all wrong.
It's not right. It's all wrong. And so at that point I was like kind of stressed out. I was like, I'm never going to be able to graduate. And so what we then did was said, well, how do we prove to them that these motions are realistic? and how do we prove to them that actually these motions can be very damaging?
Very, very bad.
And so we did this multiple ways. Like I have an entire chapter in my dissertation where I went to Japan, because Japan has large basins and they have large magnitude earthquakes. And so we looked at ground motions in Japan, and we basically quantified basin amplification in Japan, and we compared it to the basin amplification that we were seeing here. And so when we presented that to the engineers, they were like, okay, now that makes sense. And then we, when we said, okay, let's now see what the building response would be, I wanted to do one building and be done. But then they were like, well, you know, it's very hard to really understand the effects if you just do one building. And then we already do really complicated analysis for tall structures. And so we know what's happening to them, but we don't know what's happening to all those code prescribed analyses or code prescribed designs. So what then I did was I said, okay, let's build models. And I have like a 6-hour presentation that like 100, we had like a set, like I think once we did like a workshop, and it was like a 6-hour workshop where we went from A to Z. And in one of the presentations, we looked at basically all archetypes. We looked at archetypes that were designed using these code enhanced procedures. And we looked at archetypes that were designed using code prescriptive procedures. And we showed that if you designed buildings using code enhanced procedures, like you followed the Tall Building Initiative guidelines, you did your nonlinear analysis checks, you generally saw better performance than those structures that you just used the code prescriptive procedures. And so that sort of it sort of made engineers feel like, oh, so maybe we should be doing code enhanced procedures for all the buildings in Seattle, because that generally led to better performance. And so, you know, it took a while. And so I don't know if that answers your question, but it definitely, it wasn't easy.
In terms of defining the basin, you showed that slide that had soil characteristics, something about shear wave velocity or something. How did you get that data? Like, where did this data come from?
So this data, so the USGS basically 10 years ago went and they mapped the shear wave velocity of the entire Pacific Northwest.
Gotcha.
And so they basically had these like instruments to measure shear wave velocity all across the Puget Sound region, and they had ships go along the Puget Sound and set off these small explosions, and they measured the time it would take from the explosion for the waves to go from the explosion all the way to the sensors. And using that data, they sort of try to figure out what the basin looked like.
Gotcha.
In terms of shear wave velocity. And so it's like, that's why when I start this project, I say, oh, thanks to all these people. I could put in like another slide that talks about all the data that was used to gather all of this stuff. And so we used it's all the work here is built on previous work that was used to map the Seattle basin and the effects of the Seattle basin.
Very cool. All right.
One final question.
Yeah, go for it. Yep.
Is it possible, Nasir sir, to have your PhD dissertation? I'm not sure if it's the right thing to ask.
Already
if it's
online.
Open source.
Yeah,
it's all open source. Yeah. All my papers, all my models. I should probably say this. Yeah. Ground motions are all open source. All the models that I used in my work are open source. They're all on GitHub. My dissertation is on the University of Washington Library. All the papers that were published part of this work are now have been out, so you can actually download the paper that talks about this work. I think this one is on this particular presentation is earthquake spectra paper, and so all of this is for you to use. You can
So what
use
I'll
it,
do,
build up on it.
I'll follow.
The OpenSees material models, the OpenSees material models that I developed are all on the GitHub OpenSees page, and you can download them, you can compile them, you can use them. Maybe the next version would be ask. I need to email, or maybe you guys can email the people that compile OpenSees Pi and get them to write the Steel O2 fatigue and and Concrete O2 IM or IS, I think, initial stiffness.
Yeah, yes.
Yeah.
So what I'll do is I'll follow up maybe tomorrow with an email that has links to all this stuff to all you guys so that you can access all this really easily. So it'll be linked to Nasser's GitHub and then links to his dissertation and all these papers. It's all really good work. It's yeah, all this stuff's really, really great. So I guess with that, Nasser, we'll close your presentation because like I said, I've had to cancel a few meetings because this has gone on for so long.
Oh, sorry about that.
No, all good. Oh, this is way more interesting. So in terms of just some bookkeeping with regards to this group, it sounds like Pavan's been getting some feedback that you guys would be interested in doing something more workshop type focused, where maybe we can do some hands-on, like develop a model and do some IDAs, or that's passé now, maybe some multiple stripe analysis together, if you'd be interested in that. So I think maybe in a month or so, we'll try to have like more of a workshop. So instead of a presentation and discussion, we'll actually go through, how to set up a model, how to do collapse analysis, things like that. It sounds like there'd be some interest. Another thing that I think would be interesting is we haven't had any geotechs really. So maybe we'll try to find a geotech to give a presentation, because I know there's been some really interesting work there. So I guess with that, does anybody have any comments, final comments? Great. Well, thank you guys so much. Yeah, Nasser, if you want to hang out for a second, if everybody.
Sure.
Thank you. Thank you. That was very interesting. That was very helpful.
Yeah. Thank you for having me.
Thank you very much, sir.
Thank you very much.
You're welcome. Take care.
Thank you very much,
Nice
sir.
meeting you all. Thank you.
Thank you so much.
You're welcome.
Dude, that's 2 hours long. Holy crap.
I know. Sorry for going over. I
No,
guess I didn't.
super interesting. Super interesting. I think that was really, really
I kind of gave the. So I remember Jeff once asked me to do this presentation, to do a presentation on my research for Earthquake 2, and I took all the slides that I've ever made in my dissertation from A to Z, and I made it into one big PowerPoint. And and Earthquake 2 is a 2-hour class. And I took 2 sessions. So it would be like a 4-hour presentation on like from A to Z. And I did it. And I did like not the conference presentation where you're just like, oh, we use this, boom, boom, boom. Like actually stop and just talk about each step and why we did what we did. I mean, the students asked questions and a lot of them were interested. And so the animations help to make it a little more entertaining. But yeah, it's
great.
In talks that I give to outside people, even in job talks, like I give them like a 45-minute version. I cut a lot of stuff out.
Yeah, that was great. That was awesome. Cool.
Yeah.
Cool. Thank you so much for doing that. I'm probably going to ping you with an email so that you can point me to all the relevant stuff. I think I have a lot of
Yeah.
I'll probably
I can download whatever is missing and send it to you, and then I can also send you links to the GitHub stuff. It's all on my GitHub page, so if you go to my GitHub page, you'll see it.
Yeah, I'll just point them
And
to that.
You'll probably need a link to PNet, which is the UW repository for the M9 motions. So I'll send you that too.
Yeah, that'd be sweet.
And then hopefully that helps. Yeah.
Cool. Oh, that sounds good, man. All right. Well,
Cool.
I should probably go to bed. I could tell you're getting more and more tired as it went on.
Oh my God. I towards the end, I was like, what was I gonna say now?
I know, yeah, I could tell.
I'm like, and then I started saying like things that were, you're still recording, but anyways, if you can cut that out. But
I'll cut this part out.
yeah, but yeah, I was like saying stuff and I was like, wait, no, that's not the word that I wanted. I want to use this word.